So what we're going to look at is we're going to take a look at polynomials. And you've seen polynomials before. So for example, say something like this. This is a monomial and got one term. And you've probably seen binomials, of course. Going to have two terms. And then you're going to have trinomials. And the thing with these, what we see with these different polynomials, whether it's a monomial, a binomial, or trinomial, what we have are the terms are separated by plus and minus. And in general, this is what we have for polynomials. This is the form, and it's going to look something like this. Now I want to talk about a little what's going on here. These n's up here, these are for exponents. So for example, for this one, n would be 2, 2 minus 1 is 1, and then we have a sub 0, which is our constant. Now, the exponents for polynomials, they're whole numbers. So whole numbers are numbers we count on our fingers. So like 1, 2, 3, and so on. We're not looking at numbers that are fractions. We're not looking at numbers that are decimals. We're not looking at numbers that could be negative. For the exponents, we're looking at whole numbers, 1, 2, 3, 4, 5, and so on. Now, these numbers in front, those can be real numbers. They're called coefficients. These are real numbers, and so these could be anything really other than imaginary numbers. So exponents, whole numbers, and that's it. And then for the coefficients, any real number you want. All right. So to kind of break down the notation here, what you're seeing, the n here, for example, or the n minus 1, that's an exponent, so that's going to be a whole number. This here is an index. Now it's also a whole number, and we make sure that it matches the exponent. But let me kind of go over what's going on with that. So if we have this, well, in this case here, a sub n, well, it's going to be a sub 2, and that's 3, and it's going to match with the exponent. So a sub 2 is going to be 3, it's matching with the exponent. A sub 1, again, matching with the exponent, it's -7, and then a sub 0, our constant, well, that's just +4. So that's a little bit about how the notation works. Another example with these, let's say we have some numbers here. Let's say we have, let's not do a list or a set. Let's say we have -2, 7, 6, 8, and pi. Let's say this is a list, and this is some kind of order. This is the order we've got. Granted, it's not exactly a numerical order, but okay, but that's, say this is the output from some function. Well, a sub 1 would be, say, -2, our first number. A sub 2 could be 7, and then 1, 2, 3, 4, 5. A sub 5 would be pi. And so this is just saying that we're referring to some, this could be list A, for example. And this is the first number in list A, the second number, the fifth number, first, second, and fifth. With polynomials, we order them backwards. We start with the largest index and then go to the smallest. All right, so that's some, hopefully that helps a little bit with indices. If you have any questions, let me know. So what we have with polynomials is they're made up of terms. And typically what's in a term is some coefficient in front and then some kind of exponent, like so. Or we could have multiple variables. So we could have, say, a coefficient in front, a variable with an exponent, like so. We have a couple variables, and these two exponents don't have to be the same. So that's the idea of terms. And in a polynomial, terms are separated by plus and minus. So we add and subtract the terms together. So for example, you'd have a polynomial p of x and p of xy. Let's say we have two variables. So you have 6x squared y cubed plus 7x squared and minus 8. And each of these are terms in the polynomial. And again, you could have a constant term. It doesn't always have a variable attached to it. All right. So we can talk about the degree of terms. So the degree of a term works like this. It's the exponent on the variable or the sum of exponents if there's multiple variables for this one term. So for example, well, just to reiterate again, it's the exponent on the variable or the sum of exponents on those variables. So let's say 6x to the fourth. Well, the variable on here, or sorry, the exponent on the variable is 4. So the degree is equal to 4. And then for this one, x squared y7, the degree, we add up the exponents and we get 9. Now, when you see a variable without an exponent, it actually does have an exponent. So if you have something like this, well, the degree will be 2, and there's an invisible 1 is what's going on here. There's an invisible 1. And so it becomes 3. Finally, the degree of a constant term for this, the degree is 0. Constant terms have a degree of 0. All right. So let's say there's a term, there's going to be the case here actually. There's some term, of all the terms in a polynomial, there's going to be a term with the highest degree. So this is the leading term. So it's the term with the highest degree. So for example, and let's have a polynomial that's not in standard form. Well, the term with the highest degree, if we take a look at the degrees of each term, this is a degree of 1. This is a degree of 2. And this is a degree of 0. So the leading term in this case, highest degree, going to be that, the x squared. And then usually with polynomials, we put them in standard form so that the lead degree or the lead term goes first, and then terms with smaller and smaller degrees follow. So standard form for this would be x squared plus 3x plus 2, or the degree 2, the degree 1, and the degree 0. Well, attached to the lead term, there's usually a coefficient. Now this one has that invisible 1. Whenever you have a variable expression that doesn't appear to have a number attached to it, actually it does. There's an invisible 1 because there's 1 of the x squareds. So it's the coefficient of the lead term. Now this is going to become important later. When we get into graphing this lead coefficient and the exponent of the lead term, those are going to be very critical. Anyway, so let's take a look at one last thing here. The degree of a polynomial. So the degree of a polynomial is the same as the degree of the lead term. It's the same as the degree of the lead term. So when you want to find the degree of a polynomial, just look for the lead term, and that's the degree of your polynomial. You don't want to add up the degrees of all the terms. You don't do anything like that. Again, find that lead term, find its degree. That's the degree of your polynomial. So for example, I'm going to make this a minus here. So again, we look for the lead term. That's the term with the highest degree. Degree 0, degree 7, degree 2. Well, there it is. That's the lead term. and its degree is equal to 7. So that means the degree of the polynomial that's equal to 7. All right. So that's sort of our introduction to polynomials. Now we're going to talk about graphing them. The first thing we're going to talk about, before we get into specific points, is general appearance. And polynomials, they're smooth and continuous. They're smooth and continuous. So basically they look sort of like this. Now this is just one version of a possible polynomial. They could have lumps, they could be doing all kinds of things, but typically they'll either dive to negative infinity or maybe shoot up to positive infinity. But they do all kinds of crazy things in the middle. So things that you're not going to see in a polynomial. They're smooth, so that means there's no corners. So polynomial won't do something like this. You're not going to see something like that or something like that. You won't see something like this. In these cases, not for polynomials, not for polynomials, not for polynomials. Also, there are no gaps or discontinuities. So that's why it's continuous. So you're not going to see stuff like this. And you're not going to see stuff like this, like think of 1 over x. So 1 over x, you get that vertical asymptote that splits the function into 2 branches. You're not going to see that either. So stuff like this, you're not going to see that. So we're going to see something smooth, but that's kind of about it. Like what happens in the middle of these polynomials, could be all kinds of stuff. And that's why these can be very tricky to graph. When you get to calculus, we'll have more tools to graph polynomials. But this gives you a very rough idea. No corners, no gaps or discontinuities, no vertical asymptotes. They eventually tend to take on a consistent direction after a while, either this way or maybe this way, or they'll come in from here and then shoot down here again. But there's all kinds of stuff that can go on in the middle. So let's talk about what's happening on the ends here. There is some consistency there, and it has to do with that lead term. So the end behavior is what happens when x gets larger and larger or farther down the positive x-axis, or if x goes the opposite direction, farther and farther down the negative x-axis. Eventually what your polynomial will do at these extremes, it'll either continually rise forever or it'll continually drop forever. Well, excluding the constant polynomial, which is just flat forever. But if it's not constant, it's either going to be going up in one direction or dropping down, or going up or dropping down, but it's going to choose one or the other, up or down at the extremes. So let's see. Well, how do you figure this out? Well, it has to do with the lead term. And we're going to talk about what is special here. Now, the thing we're going to look for is this. The lead coefficient, I'm going to abbreviate that LC. Is it positive or negative? And is the exponent even or odd? This is our lead term. So what determines end behavior is whether or not the lead coefficient is positive or negative, and whether the exponent for this lead term is even or odd. This is called the lead coefficient test. So let's take a look. We're going to be looking at combinations of even or odd exponent with positive or negative lead coefficient. So I'm going to break this up like this. So let's say we have n is even in this column. Here's n is odd. And here's a sub n equals positive, a sub n equals negative, a sub n equals, well, let's see, we gotta mix this up a little bit. Let's say this will be negative, we'll make this one positive. A sub n equals negative. So we have all possible combinations: even positive, even negative, odd positive, odd negative. And again, we're thinking about this term. And this is our lead term. So in the middle, again, we don't know what's going on. Big question mark. But when you have an even exponent and you have a positive an at the extremes, our polynomial does that. Now, if n is odd and this is positive, again, we might not know what's going on in the middle, but at the extremes, at the infinities, we're going to get something like that. Now, if n is even and an is negative, again, not sure about the middle, we're going to get something like this. Oh, sorry, this is even. I'm going to do this. Both of them drop down. And then for n is odd, we're going to get something like that. So this is the general, very, very general look of our polynomials. It's not as exact as, say, the canonical functions like y equals x squared, y equals x cubed, y equals absolute value of x. There could be all kinds of moving around in the middle here, all kinds of ups and downs. But once we head out towards the infinities, for this being even, this being positive, it eventually just shoots up. And then we see different behaviors depending on if n is even or whether or not an is positive or negative. Or this could be odd and this is positive or negative. So this is we can make consistent assumptions about these polynomials at the extremes. The middle's still going to be a mystery. And so what we're going to do is try to pick apart that mystery as best as we can. We're going to have better luck with this in calculus. In calculus, we'll be able to find the minimums and maximums of this thing, or relative minimums and maximums. That'll help us draw it maybe a little more precise, but we're going to do the best we can. And we're going to work with x-intercepts and y-intercepts. Now, the y-intercept is, we're used to working with y-intercepts. It's where this polynomial crosses the y-axis. And when it crosses the y-axis, x has a value of 0. So to find the y-intercept, we find p of 0. And so what we'll get is the point 0, p of 0. Because remember, we let x be 0. And we'll get some p of 0, which might be a number that's not 0, could turn out to be 0. So for example, so we let x be 0. So when we do that, we get p of 0. And you're going to get 1. So we get 0, 1 as our y-intercept. And so that's it for the y-intercept. So that's not totally too complicated. It might be a little bit, but practice makes perfect. So where it's going to get a little messy is the x-intercept. So with the x-intercept, we're going to let y equals 0, or for us, that's going to be p of x equals 0, and solve for x. So where this can get a little tricky, it depends on the polynomial you're working with. If you have a quadratic function, use a quadratic formula. That's a great way to do this. Or we're going to do a lot of factoring. So factoring can be really big in this. So let's say we have this. Let's see here. Find a good polynomial to factor. So for something like this, we can try factor by grouping. So we'll know if factor by grouping worked when we get binomials in one group and the other, that they're the same. So I'm going to scope these first two and then these second two. I'm going to ask, what can I extract from both of these terms? And the fact that I can extract the same thing from those two terms makes them a group. So I can extract from both of these an x squared. So they're the x squared group, because I can get an x squared out of here and out of there. From this one, from both of these, we can extract a -4. So this is the x squared group, that's the -4 group. So let's do these extractions. And we're setting this equal to 0. You want to remember that we're setting this equal to 0. X squared, x plus 7, minus 4 times, let's see, that'll be x plus 7. And you can check the math here. Distribute this to here and to here. You'll get those two terms again. Take this -4, distribute it to the x and to the 7. You'll get those two terms. So, okay, we've done our, well, we factored out a bit. Did this work out? Is it correct? Well, this binomial is the same as that one. That means factor by grouping did work. So we factor this out. And this is what's called the difference of squares. So this means we can write it like this. It's one of those special forms. Another way you could do this is you could solve for x. You could take x squared. I'll get to that in a little bit. What we want to look for is, since this is set equal to 0, what numbers that x takes on that makes this whole thing 0? Because this times this times this equals 0 only happens if one of these is 0. The only way you can get something to become 0 through multiplication, one of the things being multiplied has to be 0. Could be this one, or this one, or all of them. So we kind of presume all of them. We want to find all the x values that can make this whole thing 0. So for this to become 0, we find out x needs to be -7. Okay. For this to be 0, we find out x needs to be -2. All right. For this to be 0, we find out x needs to be 2. So what have we figured out here? When we let y, or p of x, be 0, we get 3 x's that make that happen. That means we had 3 x-intercepts. -7, remember y is 0. -2 and 0, and 2 and 0. This means this polynomial contacts the x-axis at 3 different points. Now notice I said contacts, I didn't say crosses the x-axis, because to be honest, when we talk about these in the past, that's kind of what we said. The polynomial would cross the x-axis completely. But what we're going to find out with polynomials, unlike lines, is they'll actually cross over. They don't always cross over. They'll sometimes just hit the x-axis and bounce off, kind of boop, boop, like that. So that brings up something called multiplicity. Now I do want to mention something. If you didn't see this difference of squares, which you could have done, is you could say, well, all right, x has to be -7 for this one. This, let's see, x squared minus 4 equals 0, x squared equals 4, x equals plus or minus 2, and that would also give you those 2 other zeros. -7, +2, -2. Could have done it that way also. All right. So this brings up an issue, multiplicity. What is multiplicity? Well, sometimes a 0 or a root is there's multiples of it. So for example, p of x equals x minus 2 cubed times x plus 4. If we expand this out, we have multiples of x minus 2. So if we were looking for the zeros, we have this. And you could rewrite this as 3 x minus 2s, all multiplied together. So what we have is this. This becomes 0 only at x is 2 and 0 and -4 and 0. Because if you plug in 2, makes everything 0, plug into everything 0, plug into everything 0, plug in -4, then everything becomes 0. There's only two numbers that make this whole thing 0, 2 or -4. So there's a way we interpret this that's really important. We say this here, because it's repeated 3 times, and we don't have to expand it out. We can just note 3 times. So whether we look to the exponent or whether we look at the thing expanded out like this, there's going to be 3 2's that are going to be zeros, 3 x minus 2's, and each x minus 2 becomes 0 when x is 2. So we say that this has a multiplicity of 3. And this here has a multiplicity of 1. I'll abbreviate multiplicity here. So that's what we've got. Multiplicity of 3, multiplicity of 1. So what's the big deal with multiplicities? Well, in polynomials, if you have an odd multiplicity, it means you do cross over the x-axis. You'll punch right over it at that x-intercept. So with odd multiplicity, and that can be multiplicity of 1 or 3 or 5 and so on, it's actually going to cross over the x-axis. So here's your x-intercept. Your polynomial will do something like this. Or maybe you'll do something like this. But it'll cross through the x-axis at that x-intercept. Now, if the multiplicity is even, if the multiplicity is even, p of x bounces off the x-axis. So it might do something like this. Or you might see something like this. Now, there are two sort of classic examples of this, and it has to do with x squared and x cubed. So let's look at the canonical function, x squared. We can rewrite this as x minus 0 squared. which is perfectly fine. So for what value of x does this whole thing become 0? Well, when x equals 0. So that means the x intercept is x equals 0. So you could say that, x minus 0 equals 0 or x equals 0. So the x-intercept is x equals 0. Now this x-intercept has a multiplicity of 2. So take a second to kind of absorb this for a bit. You can take x squared, rewrite it as x minus 0, because x minus 0 is just x. And then if just x, you square it, you get x squared. Takes it back up to here. But we could just leave it like this because this looks like a factor. Not a very impressive one, I guess. All it's saying is, well, okay, when is this equal to 0? And then, well, it's just when x equals 0. I mean, if x was 2, you'd get 2 squared, and that's not equal to 0. X was negative 2. Negative 2 minus 0 is negative 2. Square that, you don't get 0. This only equals 0 when x is 2. I'm sorry, 0. Now, it has a multiplicity of 2. So that means it should bounce off the x-axis at x equals 0. And sure enough, when you think about the graph of p of x equals x squared, which is the same as p of x equals x minus 0 squared, sure enough, it bounces off the x-axis, like so. So let's take a look at another one. Well, p of x equals x cubed. Now again, we can rewrite this as x minus 0 cubed, because subtracting 0 again doesn't change anything. And if you can go backwards, x minus 0 is just x. We're cubing that, we get x cubed. But again, we can try to find the x-intercept. When is this equal to 0? Well, when x is equal to 0. So there you go. But here's the thing. This here is a multiplicity of 3. So that means at x equals 0, which is going to be the x-intercept, this passes through the x-axis. And sure enough, if you recall x cubed, what that function looks like, sure enough, it cuts right through, goes right through that x-axis at x equals 0. So again, odd multiplicity function will go right through x-axis at the x-intercept if that x-intercept has an odd multiplicity. If the x-intercept has an even multiplicity, it's just going to bounce off. All right. There's one last thing there's a couple things to mention. And it's a property of the fact that these are smooth functions and they're continuous. That means there are no gaps and there's no discontinuities. So there's no hops, no leaps the function's doing. And this is called the intermediate value theorem. The intermediate value theorem. Now let me pull up their exact definition, but roughly speaking, it's this. If you have a function that's below the x-axis, and then later down the line, it's above the x-axis, and this is a function without gaps, without discontinuities. It's got to be smooth, everything's connected together. If it starts out below the x-axis, and then later it's above the x-axis, it had to have crossed the x-axis at some point. So let me get the more precise definition here. So if P of A and P of B have opposite signs. In other words, one is positive, the other is negative. If they have opposite signs, then there is at least, there could be more than one, between A and B, where P of C equals 0. So there's at least one. Now let's say there's just one. What that's saying is that if you have a polynomial passing through this point, and this point, then somewhere in the middle, somewhere along in here, there's at least one point where this polynomial crosses this x-axis. So there's some point C, at least one, there could be more, where the polynomial is crossing the x-axis. So when you're drawing your polynomial, if you're, for example, experimenting with points, let's say you just come up with some inputs, compute some outputs, and plot the input versus output. And you notice that you have some points below the x-axis and some points above the y-axis. And this is a polynomial. There's no gaps or jumps. That means there must be some x-intercept. And that's one way of telling that you do have an x-intercept. So there's that. And it could be doing a lot of things. Like you could have, for example, multiple x-intercepts. You could have a situation like this. There's P of A, P of B. This polynomial could do all kinds of crazy stuff like this. For all that we know, there could be multiple x-intercepts for this polynomial. So we're getting some idea of what's happening in the middle. We looked at end behavior, and we can make some consistent assumptions about our polynomial at the infinities, whether it's going positive infinity on both sides, or maybe positive infinity and the negative infinity, maybe that's switched, maybe it's both negative infinities. We can make some general assumptions on the infinities. In the middle, it's a little tricky, so we can find maybe x-intercepts, y-intercepts. We can look at the multiplicity of the x-intercepts to see if the polynomial is passing through the x-axis, if it's an odd multiplicity for that x-intercept, if maybe a different x-intercept for that polynomial has even multiplicity, well then it's just bouncing off. The x-intercept doesn't cut through it. We can use the intermediate value theorem to look for regions where there's probably some x-intercepts. If we have P of A negative and P and B positive, between A and B, there's got to be at least one x-intercept. Could be more. Finally, there is a little more help we get, and it's what they call turning points. And the guideline here is this. If your polynomial has degree n, it has at most, we'll talk about what these exactly are, n minus 1 turning points. Has at most n minus 1 turning points. So what that means, what is a turning point? Well, we graph our polynomial, we see it do something like this. And then here it takes off for infinity very slowly to negative infinity. This one rapidly shoots up to positive infinity. But these here, these are called turning points. In calculus, you'll call them relative minimums and relative maximums. But those are the turning points, and there's 4 of them here. So what this says is this. If we have our polynomial and we're trying to graph it, and it has a degree of, say, 5, then the number of turning points it can have at most of, could be less, could have fewer. The biggest number of turning points it could have would be 5 minus 1, or 4. Now, it could have 3, it could have 2, it could have 1. So for example, here's one that sort of maxes out turning points. So we have x squared. Again, now the degree in is 2. So the maximum amount of turning points is n minus 1, or 2 minus 1, or 1. The largest number of turning points this polynomial can have, or monomial, is 1 turning point. And sure enough, that's the number of turning points it has. If we graph it, we get that. There's 1 turning point where it comes down, turns around, goes back up. So this one maxes out the number of turning points. Now, one that doesn't do this is x cubed. Take a look at this one. So we've got x cubed. Now, n in this case is 3. So n minus 1. So this could have at most 2 turning points. So how many does it actually have? Well, a little disappointing. It doesn't have any. We get here, and then it levels out, and then just keeps going. So we don't get any turning points out of this one, just keeps going. So, well, there you go. Now, it turns out, though, with x cubed functions, you can play around with them, include different terms and things like that, like x cubed minus 2x squared plus 3x minus 4. And you can get them to look kind of like this. And so you'll get a couple turning points, say one here and one there. So as you play around with functions that have a lead term of x cubed or a degree of 3, you can get functions that have 2 turning points like that. All right. So just as a note, if you do calculus, if you take the derivative of this, because oftentimes where we get turning points in calculus, we take what's called the derivative, we set it equal to 0. A derivative is a special modification of the function's terms. Set that equal to 0, solve for x, you'll get the location of these turning points along the x-axis. If you do the derivative for x cubed, you'll also get a location here at 0. But we don't have a turning point here. We just keep going. We just sort of slow down, but we'll keep on going. All right. So let's take a look. So finally, what you can do for these is you can always test for symmetry. And what you can do in symmetry for these, it's kind of hit or miss. A lot of times when you do symmetry tests, you're going to get no symmetry at all. In the two symmetry tests, we're looking for symmetry across the y-axis, symmetry across the origin. Or what we're looking for, f of minus x, or sorry, we'll stick with p, just gives you p of x when you simplify it. So this is the y-axis symmetry. And then if it's origin, you'll be able to factor out that minus. And you'll get minus p of x. But very often what you're going to get is neither. And sometimes symmetry can help, but let me go through an example with symmetry here. Let's say we have this. So let's say we have something like this. So the way you test symmetry, you put in p of negative x, and this will simplify either to just p of x, the negative sign just gets away, disappears. Like if you square the negative sign, it goes away. If you take the fourth power of a negative sign, it goes away. So the negative sign just dissolves into the polynomial. Or it hangs around where you can factor it out, and it's just the minus sign times your polynomial. You can factor out a minus sign. So again, this is going to be y-axis. This is going to be origin. The other option is you get neither. You don't get this, you don't get that, so there's no symmetry about the y-axis or about the origin. So just to kind of get an idea of what it looks like, this is p of x. Minus p of x will look like this. So for testing for symmetry, it doesn't hurt just to see what this looks like. Minus x cubed, minus x squared, minus 3. So this is what we're going to do. We're going to plug in negative x. And when we simplify everything down, if we get this back, we're symmetric about the y-axis. If we get this, though, we're symmetric about the origin. If we get neither this or this, we don't have symmetry across the y-axis or the origin. And we don't worry about symmetry across the x-axis. Polynomials are functions, and remember, symmetry across the x-axis means they're not a function. So we're not going to worry about that. It doesn't apply. So let's see. Negative x, oh, sorry. So we're started with this. Negative x cubed plus negative x squared. Again, we're taking p of x, we're plugging in negative x. We just have plus 3. So this has become negative x cubed. So starting to look like this one. Draw a line here. But then we get plus x squared plus 3. So we put in negative x, and we got this. Now this is not the same as that. This one doesn't have a minus sign. And this is not the same as that. We're missing these two minus signs. So guess what? There's no symmetry. It's a neither. All right. So lastly, let's actually graph one of these things. So I'll follow the steps in the text here. So let's say we have this. So what the text recommends doing first is the lead coefficient test. So I'll abbreviate this. So we want to look at the lead term, which for us is x cubed. And let's take a look at the exponent and the coefficient. And remember, this is really 1x cubed. So this is our lead term because this is the degree 3, degree 2, degree 1, degree 0. Term with the highest degree is the lead term. So that's x cubed. X cubed is just 1x cubed, same thing. So the lead coefficient is positive and the exponent is odd. So if we look at our little table with a lead coefficient that's positive and an exponent n that's odd, I think we call this an. So lead coefficient's positive, exponent is odd. That means we have this. So ultimately, our polynomial is going to look something like this. The thing is, we don't know what's going on in the middle. We got to try to figure that out as best as we can. So I'm going to put that off to the side here. So we know it's going to look like this. So let's find the x-intercepts. So that means we're going to set p of x equal to 0, solve for x. Again, I'm following the steps of the text. So 0 is x cubed plus 2x squared minus x minus 2. And let's factor by grouping. I'm going to try it the way it is. Now, again, if I don't get that same binomial in the two places, the grouping didn't work, so I might come back to this, switch around the terms, and try grouping two different terms for each group. So let's see. Well, let's try this out as it is. So what can we extract from these two terms? And what we can extract is an x squared. Both of them contain an x squared. And these two terms, we can pull out a -1. So you have the x squared group and the -1 group. Now, when we do those extractions, we're going to get this. Oh, that's a plus, actually. If you distribute this, you'll get minus x and minus 2. So sure enough, same binomial in two places. That means it worked. So we have x equals x plus 2. We factor out the common binomial, x squared minus 1. Again, this is a difference of squares. Or what you could do, you could just set x squared minus 1 equals 0. X squared equals 1. X is plus or minus 1. And that would give you two roots. But I'm going to break it down using difference of squares and get the same thing. Now remember, when we're finding the x-intercept, we've let the y be 0. So what this means, we'll get this. And so solving for x, we get -2, -1, and 1. So that means our x-intercepts, we have 3 of them. -2, 0, -1, 0, and 1 and 0. So now that we have this, let's check the multiplicity. So the multiplicity on these, we want to see if there's multiples of them. Well, there isn't. There's 1x plus 2, 1x plus 1, and 1x minus 1. So that means x minus 2 multiplicity is 1. x minus 1, multiplicity is 1. X equals 1, multiplicity is also 1. So what that tells us is through each of these points, we're going to see the function cut through the x-axis. It's not going to bounce off. So again, because there's one x plus 2 that has an x minus 2, that, let minus 2 plus 2 gives you 0. One of these, one of these, one of these means we have one x-intercept, one x-intercept, one x-intercept, multiplicity 1, multiplicity 1, multiplicity 1. So that's what we've got. Anyway, so now the y-intercept. So looking for the y-intercept, we just let x be 0. So p of 0, 0 cubed plus 2 times 0 squared minus 0 minus 2, 0 plus 0 minus 0 minus 2. That all comes out to minus 2. So for the y-intercept, let x be 0, we get negative 2. And for this, there's no multiplicity. You have to worry about that. Only for x-intercept. All right. So symmetry. Is there any symmetry here? Well, again, let's take a look at p of x. We have p of x. And a negative p of x, we'll get minus x cubed. Just distribute a negative 1 through the whole thing. So we'll get minus 2x squared plus x plus 2. So when we compute p of minus x, so when we insert p of minus x and we simplify, if we get this back, we have symmetry across the y-axis. If we get this, we have symmetry across the origin. So plugging negative x into p of x, the square takes out the negative. Negative is positive, and we still have a minus 2. So right away, it's not the same as just plain p of x. When we give p of x a negative x, we get a negative on this x cubed. So it's not the same as this. So we don't have symmetry across the y-axis. But let's compare it to this. It's like, well, no, it doesn't match this either. Neither here. So our symmetry is neither. So we have no symmetry. Finally, we can take a look at the number of turning points. The degree n is 3. So at most, there'll be n minus 1 or 2. I'll just label it TP for turning points. There'll be at most 2 turning points. And those are going to be the 5 steps. We know generally what it's going to look like. We're just not sure what's happening in the middle. We found the x-intercepts, and we know the multiplicity for each one. We have a y-intercept. There's no symmetry for the y-axis or the origin. We can have at most 2 turning points. So let's use this to try to graph the thing. Well, at first, let's put in all of our intercepts. Let's do that. So we have a y-intercept at 0, negative 2. It's going to be right here. We have an x-intercept at negative 2, 0. We also have one, let's see here, negative 1, 0. So I get kind of packed in here. And then we also have one at 1, 0. So let's get all of our intercepts first. We've got our y-intercept, and we have our 3 x-intercepts. So we've got these, there's no symmetry. There should be at most 2 turning points. We'll keep that in the back of our heads to make sure this is turning out okay. Let's take a look at this. What we know is that as this thing comes in from infinity, it's going to come from below. So it's going to do this. And then it has to cross the x-axis. And the first place it can do that is this first x-intercept. But then somehow, I guess it's got to come back around because it's got to go through this x-intercept. And again, we're graphing this from left to right. And then, well, we've got to go through this, and then we've got to go through this. And then once we've gotten through all the intercepts, this thing just takes off for infinity. So it does something like this. So we've gone through our x-intercepts, and sure enough, we're passing through each one because each one had an odd multiplicity. If it was even, it would say bounce off, it wouldn't pass through. We went through our y-intercept, that's good. This does appear to be the end behavior. And then finally, if we think about turning points, there has to be a turning point here. If it's coming up through here and it's going to pass through this point, it's got to come back around. And there's a turning point. So we have 2 turning points, and that keeps us within our limit. So there we go. There's the graph of our polynomial. So if you have any questions about this, let me know. Otherwise, have a wonderful evening.